Next thing we're going to talk about, in addition to making inferences, is how we can have confidence intervals and other objects about our mean vector. And specifically, we can actually have confidence regions in multivariate analysis. So what we can do is plug in our t-squared value into our constant distance formula and use that to generate a constant distance for a sampling distribution. So remember that t-squared is proportional to f. So to get our 95% confidence interval, we need the t-squared value that is associated with the 95% probability on the f distribution with p and n minus p degrees of freedom, which we get this way. And then we can plot this as a constant distance along the eigenvalues and eigenvectors of our covariance matrix, and we can get a confidence ellipse. And so here's the formula. Just like before, we have the square root of our eigenvalue, and we have our eigenvector, but we're multiplying it here by the t-squared value associated with f for our alpha, which is, again, usually going to be 0.95. So here, instead of looking at actual full data, we're just going to look at a mean vector x bar and a covariance matrix S, and we're going to say we have 100 observations, just hypothetically. So this is a bivariate case, which again is going to be helpful because we can plot a bivariate case and visualize it easily. And so we're just going to assume we have a sample of 100 observations, and this is our mean vector and our observed covariance matrix. So I'm just going to create these objects first. So I'm going to create just my covariance matrix just by writing it as here, and my mean vector, writing it as here. And of course, I am going to create n and p. So next I'm going to get my eigenvalues. So this is just like what we saw last week. I'm going to get my eigenvalues from my covariance matrix and my eigenvectors. And then I need to get my critical f statistic. So this is the value of f that would be at exactly alpha equals 0.05. So I can do that with the qf function. So I have to take 1 minus alpha as the first argument, and the 2 degrees of freedom as the second argument. So here I'm taking 1 minus 0.05, and then p and n minus p for my degrees of freedom. So it turns out that f value is about 3.09. So now I can get my constant distance, c squared, by using my f and p values. So here I'm going to multiply p times n minus 1 divided n times n minus p, which is the formula that we saw before, by my f value. So that's really a t statistic. So now this is a t squared statistic. That can be our constant distance. So this is essentially what we're using as our c here, or our c squared. And then I'm just going to plug that in as c squared into my distance formula, just like we saw last week. So I plug that in here, multiply it by square root of lambda, just take the square root, multiply by the square root of lambda, and multiply by my first eigenvector. And so this is one vector that I'm going to plot, and then I'm going to do it for the second one. That's the second vector that I'm going to plot. And so just like last week, we can plot our ellipse along this. And so this is a 95% confidence ellipse based on these parameters, if we assume that we had 100 observations that produced those observed parameter values. We can use this confidence ellipse to get simultaneous confidence intervals for each of our variables separately. And so we define the simultaneous confidence intervals as the maximal boundaries along the ellipse for each individual variable. So in this case, the x and y axis. So we can think of the 95% confidence interval for the first variable as the minimum and maximum values of x1 contained by the ellipse. And we can think of the 95% confidence interval for the second variable as the minimum and maximum values for x2, which is along the y-axis here, along the ellipse. And so here, this is visualized. So here, the green lines are represent the 95% confidence interval of x1, and the red lines of x2. So we see the first variable would go from a little higher than negative 2.6 to a little bit to about negative 1.45. We can represent this mathematically with this formula. So note that we only really need the Pn the x bar of our variable and the variance. So we don't need the covariance actually for this. Here x sub xi is the mean of variable I, and SII is the variance of variable I. And so we multiply the square root of the variance divided by n by the square root of our t squared statistic, and we just take that, either add or subtract that from our mean, and that's our simultaneous confidence interval. So for our example that we're using, this is how we can obtain it. This is just the same thing written in our code, and so this gives us our two confidence intervals. So you see here, I'm using the first mean and the first variance. S11 is the first variance, and here I'm using the second and the second variance, and that gives us another one. And so for reference, here's our plot. And so again, we can see, just like I said, the green line goes from about negative 2.55 to about negative 1.45, just like you see here. And similarly there for the red line, goes from about 3.5 to about 4.5, just like we see here, 3.5 to 4.5. So we can compare these confidence intervals to what we would get if we looked at each variable separately. Remember, these are simultaneous multivariate confidence intervals. So we can also just use our t-based confidence intervals, treating each variable as a univariate separate variable. And this is what we've learned before. We just take the mean of the variable plus or minus t to the n minus 1. So this is the location on the t distribution for n minus 1 and for alpha, of course. So for 0.95, then we divide by the square root of the variance, we multiply by the square root of the variance divided by the sample size. And so we can use the QT function to get the region of the t distribution for a given degrees of freedom. And we need to reference 1 minus alpha over 2. Remember, we need to divide alpha by 2 because to account for the two-tailed test here. So here I'm taking QT, 1 minus 0.05 divided by 2. So this gives us the region of the t distribution that we're looking at, our critical region of the t distribution. And again, I just take plus or minus my mean multiplied by the square root of the variance divided by the sample size. So here we get our two separate confidence intervals where if we just treated each variable completely separately, I can add these to our plot and see how they compare to our simultaneous confidence intervals. And so what do we notice from this plot? So the separate confidence intervals are narrower. So they're less conservative in their precision. So it's a much narrower confidence interval. They're also not correct, and we don't typically want to use these here. Why is that? So think about if we've learned another way for helping us to account for making multiple inferences about two different means at the same time. And so a really common way to do this is the Bonferroni correction. So the Bonferroni correction divides the critical value alpha by the number of variables you have. So you take alpha divided by p. So it's really just an adjustment for alpha. And so here we would use alpha divided by 2 because we have p variables. So 0.05 divided by 2. So our actual critical value would be 0.25. And so you see here I do the exact same thing. The only difference is, in addition to dividing by 2 for my two-tailed test, I then also divide by p. And that gives us our confidence intervals that are Bonferroni corrected. And we can plot these as well. And we can see they're sort of in between the separate and the simultaneous confidence intervals. They're something of a compromise between them. And so we can compare them just in a table here. Then this is generally how this is going to go. We're going to have the separate confidence intervals being the most narrow, the Bonferroni being in between, and the simultaneous confidence intervals being the least narrow. There may be some really corner case exceptions where Bonferroni and simultaneous flip, but for the most part, this is the order that you're going to see. And so this is for the x2 variable that we used. So when do we want to use which confidence interval? First, if we're comparing more than one mean, we should generally not use separate confidence intervals. That's really only appropriate when we're considering one mean on its own. If we're interested in the unconditional confidence intervals, that is just a variable not conditional on the other variable, but we are looking at multiple variables, then we're going to want to use Bonferroni. They offer more precision than the simultaneous confidence intervals, but they're also not going to be not going to cause inflated type 1 error rates about each individual variable. So when do we use simultaneous? Really, the idea with the simultaneous intervals is that they're just a generalization defined by the confidence ellipse. The problem is we can't really define the confidence ellipse with numbers the way we can with just the confidence interval. But the ellipse actually gives us a very powerful sense of the joint confidence region for two variables conditional on one another. So that's taking their covariances into account, which the Bonferroni adjustment does not. So if you look at the plot, there's actually quite a bit less area inside the ellipse than inside the Bonferroni, the middle rectangle. So here's the plot again. So the area inside of the ellipse, this is, we have 95% confidence that this is our joint sampling distribution. So our two means probably fall somewhere inside of this ellipse. Now the ellipse does go outside of the Bonferroni rectangle here and here a little bit. So the actual extreme edges of the ellipse are larger, but the actual area within it is smaller. There's just not really a great way to define this area within it. Whereas it's easy to do so for the Bonferroni confidence intervals, since they're just lines that go from here to here and from here to here. So this is a much more powerful way to have confidence about a given pair or sequence of means. It's just really hard to represent this. And even in the bivariate case, the best we can really do is plot it. And even we can't really even do that when p is greater than 2. So we can, of course, generalize all of this to larger dimensional spaces. So here we're going to go back to one of the files we looked at in the first section, the tdat.csv. So there are 3 variables in this case. Remember, this is simulated data. So once again, I'm going to get my mean vector, and I'm going to get my covariance matrix, and I'm going to set n and p to be the number of observations or the sample size, and p to be the number of variables. And then I can just plug everything in the way I did before. So again, I try to make this code nice and generalizable. We really don't need to even change anything here. We can run this exact same code once we rename the objects, as I did here. And so we see we get our confidence intervals for our first 2 variables. Of course, we need to add the 3rd variable because we have a 3rd variable now. So we just change, the only thing we need to change are just the 3s here. And of course, there are lots of functions that are available in different packages in R for getting confidence intervals. One of them is the CI function from the RMIS package. So here we see it goes from upper to lower. I'm not sure why. I wish it went the other direction, but it gives us the same result for our first variable that we saw before. So you see 18.03 to 20.57, 18.03 to 20.57, exactly the same. So for the Bonferroni adjustment, remember the only thing we need to do is adjust alpha. So we're just dividing by p. So here we're dividing by p again. Again, we're getting our Bonferroni adjusted confidence intervals for this 3-variate data. And so if we want to use the CI function to do this, there's a second argument which just defaults to 1 minus 0.05 or 0.95. We just have to change this to adjust for the number of variables. So we divide 0.05 by p, and that gives us our Bonferroni adjustment. And you can verify that this is exactly the same as what we got before. Also note that we don't need to divide 0.05 by 2. This already assumes 2-tailed. Finally, for our simultaneous confidence intervals, this is just the formula, again, for reference. This is the same formula that we saw earlier, and we're just going to plug in our new values. Again, we don't have to change anything here. This is the same code. We just have to get a new f value, but we already got our new x bar, we got our new n, our new p, and our new covariance matrix. So all that stuff's already plugged in. So this code just runs again once we get our new f value. So those are our simultaneous confidence intervals for each variable. And there's a function in the MVDALAB package called MVCIs. There's probably some other ones too. This will give you the multivariate simultaneous confidence intervals, and it'll also output a plot, but it can only do it in 2 dimensions. So you have to specify which 2 variables you want. You just do this numerically. So here I'm asking for variables number 1 and 3 with the vars to plot function, and this gives me a confidence ellipse. And it also gives me the lines, which are the simultaneous confidence intervals. And then it, of course, gives me the confidence intervals down here.